Here I'm showing a plot of temperature versus mole fraction for an ideal binary solution. We have a liquid and we raise the temperature. Important that this plot is at constant pressure. Now as we raise the temperature, we'll hit this blue line. That's where the first bubble of vapor appears. So this is the bubble line, bubble point. And for this particular composition, this then would be the bubble temperature. And of course, as we continue to add heat and vaporize more, the temperature changes. If we look at the other case where we have a vapor, so we're at high temperature, and we lower the temperature, then at some point we hit the dew point and the first drop of liquid forms. This then would be the dew temperature for this pressure and this composition. And these two lines are just the results of Raoult's law. Let me write that down. So the mole fraction in the liquid phase times the saturation pressure in the liquid phase equals mole fraction in the vapor phase times the pressure. That's for component A. A similar equation for component B. Those two equations plus Antoine equations for the individual components allow us to generate the bubble point line, the dew point line. We have the corresponding lines if we plot pressure versus mole fraction. So this plot is pressure versus mole fraction at constant temperature. If we have a liquid at this point and we were to lower the pressure, here is where we would see the first bubble of vapor. So this then would be the bubble point line, and this would be the bubble pressure at this temperature corresponding to the graph. And for this mole fraction of 0.4, likewise this is the dew point line, and for this composition this would be the dew pressure for this temperature and composition. These two lines are also generated just using the Raoult's law equations and knowing the pure component saturation pressure.